Alright guys, welcome to Neuralist, and then this will be our first demo, and it will be Introduction to Classification with Neuralist. So classification is really where you train a model to predict what group data belongs to, and pretty much there are variables that are going to be associated with that data, and that's really the whole goal of classification. There's a wide range of practical problems this applies to. So Neuralist right now in the beta offers classification for data in tabular format, which is expected to be CSV files, which can be easily converted from Excel files just by saving it as a CSV, as well as image classification, which can be done with PNGs and JPEGs. This tutorial will focus more on the iris dataset, which is a CSV file. So what is the iris dataset? So that's a dataset that's 150 data points, and essentially they are divided into three groups with their three different types of iris plants. There's iris setosa, versicolor, and virginica. And there are four pieces of information, which the features about each flower. And so those are the petal width, the petal length, the sepal length, and the sepal width. And these are all measured in centimeters. And the goal really is to use these pieces of information to predict the type of flower just from these measurements alone. And so what you'll see in the next portion of this video is going to be a demonstration of exactly how this is done in real time, so you can see how a user would actually do this without just reading a bunch of documentation. So hope you guys enjoyed the introduction, and we'll see you in the next part of the tutorial. Alright, so now we're going to do the actual live demonstration. So here, what do we need to do to actually run this demonstration? So all we need to do is figure out, we go to our Neuralist directory, and then we type in, Python, and we do run neuralist main.py exactly as is, and then we do this /path, and then we type in, or really copy paste, the exact path where the iris demo lives in the CSV format. And really it's as simple as doing that and then hitting enter. So it takes a few seconds to load up. Okay, so now what we see here is from the CSV, we have the ID, the sepal length, sepal width, petal width, and the species. Remember, we want to actually predict the species. Before we do that, maybe we want to kind of get rid of this ID column, because it doesn't really tell us, something useful about the data, so we can just go ahead and drop it. So we can just say we want to drop one column here. So we drop the ID, and then we want to predict the species. So there we go. So this is really as straightforward as that. All we simply tell Neuralist to do here is what feature, what column specifically we want to predict. So you can really enter in any of these columns, and that's what we end up predicting. So what happens is there's one column that's chosen to be what you want to predict, and all the other ones act as variables, features that you're going to use to predict the column you selected. So of course this just for this demo, and this is sort of a little bit more obvious that we want to predict the species. Okay, so the first thing that happens is we have a class breakdown. This is a little histogram of how many samples are per class. So see there's exactly 50 of iris versicolor, 50 of iris setosa, and then 50 for iris virginica. And of course, once we're satisfied that we looked at this and we want to feel confident, then we can go ahead and X out of it. One thing that I'll mention here is that the color scheme actually changes every single time you run this script. So if you want to rerun it again in a little bit, we're going to see these colors will end up changing. It's just three colors because there are three classes in this data set, and they'll just be randomly chosen each time. So we'll go ahead and X out of that. So once we do that, the next thing that pops up for this file is, do we want to use some kind of scaling? So typically, for those of you who are new to machine learning, scaling just simply means you change the numeric value of the variables in the data just to make the models learn better. And so just for simplicity, I'm just going to pick the standard scalar, so you can just put S. I know in general in Neuralist, whenever you see a little parentheses with a single letter, that's just sort of a shorthand for executing whatever comes before it. So S is, we're going to enter an S. And now, so we're going to scale the data, and what do we do next? So now, remember, Neuralist uses random forests as a default type of model for CSVs. So what's the max depth of the trees that we want to have? Let's just say we want our trees to go up to depth 7. Let's say we want maybe 30 trees, and once we enter in this, it's going to actually run, it's going to train on the training set, and it's also going to validate the data, and we're going to see all those metrics in just a second once I hit enter. Okay, so let's walk out everything that happens. So here, we see that we actually got a perfect score on the training set. We got 112 out of 112 right, 100% train accuracy, and we got most of them right for the validation, 92%. And then, of course, below we also see a breakdown of the precision, recall, and F1 scores. And these are sort of, again, just default metrics that you have when you run this, when you run Neuralist main. Now, it's important to note that. So, how the heck do we get 112, versus 38 here? How the heck did that even happen? So, what's really happening is that actually by default there's a 75-25% training split, and test split, so that 70% of the data is used for training, and then the rest 25 is used to test it out. So that's what happened here. So let's actually run it again this time. We're going to see what else we can do with Neuralist, not just simply the default arguments. All right, welcome to part 2 of the Iris demo. So in this one, we'll be doing a different model than we did the first time. So the default model last time was the random forest, and that's going to be the default model that this always will go to unless you provide the specific model you want to pick. So the model we're going to use here is a support vector machine. We're going to do a feature analysis on the data, and we're also going to do a manifold plot. And I'll walk through all of these once we touch it. So of course the beginning part of this is going to be like last time. We're going to simply pick a column of drop. It's going to be ID. We want to predict the species. And now of course we get our class histogram. So notice that this is just like last time but with different color schemes. So we sort of see the breakdown of all the classes. So 50 of each. So I'm going to go ahead and close out of this because we saw this in the first part of the demo. And this time we're going to use a min-max scaler. So what this does is actually going to squish all of our numeric values for each feature between values that we specify. And commonly we use 0 for the low and then 1 for the high. You can do -1 to 1. It's really up to you to decide what you want to do, but 0 to 1 is fairly common, and it's certainly a great starting point. Okay, so now we plotted feature importances. So remember, in order to do that, we had to set feature analysis to true. We do -- feature analysis, with the underscore to true, and then we can see this nice little plot. So notice that the petal length and petal width are actually far more important than the sepal length and sepal width. So this tells you that you could probably get a model with comparable performance just by predicting off of petal length and petal width and sepal length and sepal width than if you did rather than picking all 4. Sorry. So these last two are almost as, you can probably pick a model that would be as good with just the last two as you would for all 4. This sort of kind of gives you a picture of how this all works, and the numbers here are from 0 to 1 in terms of importance, and then as long as you have under I believe 12 classes, it actually will display the specifics. Not 12 classes, 12 features. As long as you have 12 or fewer features, it will actually display the feature along with its corresponding importance in these plots. And again, the color scheme changes each time. And if you wanted to train a model with fewer features, because the model is very large, you have a large data set, you can kind of figure out which features you'd want to keep versus eliminate the next time around. So that's the purposes of this plot. Okay, so now for manifold analysis. Now what this does is this sort of represents the data as a 2- or 3-dimensional group of clusters, and then we're going to sort of see exactly how this all works in action in a second. So we actually have 4 types of manifolds we can choose from, but the issue is that PCA is a little bit buggy. This is going to be fixed soon, so this might be buyer beware for this one. But the other 3 work fine for 2 or 3 dimensions. So we're going to pick t-SNE for the purposes of the demonstration, and we're going to pick 2-dimensional plot. You can pick 2 or 3 and it'll work just fine. So let's just sort of give that a second to run. Okay, so here we see the clustering of the classes. So note that we have Iris setosa in black over here, and Iris virginica and versicolor in green and I guess brown over here. Now notice that this data set clustered pretty darn well. Iris setosa clustered perfectly because there's no black in the mix over here, and the other two have a slight mixing, but overall they cluster pretty darn well. And this sort of is a green flag because this means that it shouldn't be too hard to find a highly performant model for this data set. So I'll go ahead and X out of that. And of course, we're going to pick a support vector machine this time. Remember, we did that in the beginning. And of course, we're going to pick from one of these 4 kernels. And so I'm going to pick the linear kernel, so I need to type in an L. Of course, you can pick any of these 4. These are the 4 most common ones. Okay, and here we're going to enter in a C value. And essentially, you can look up exactly what the C value does, but for beginners, we sort of specified a range which users can start with. So, it's recommended to pick between 0.1 and 1. So I'm just going to pick 0.8. And then we run the model, just like last time. And so notice that we actually did very, very well. We did 96.4% accuracy on the training data and 97.4% accuracy on the testing data. And so we actually only missed 1 in our test or validation set, which is very strongly a highly performant model. So let's actually break this down. So notice that we have the precision recall scores for training and validation. Notice that in both cases, for training and validation, the Iris setosa was predicted perfectly. There was not a single misclassified example for Iris setosa. Now, notice that for versicolor and virginica, there was a few miscalculations, and that's to be expected to an extent because the t-SNE plot showed us that these classes have a little bit more mixing, so it might be a little bit harder to get perfect accuracy on them. And so that is essentially what we saw here, right before our eyes. Now, one more thing I wanted to conclude here for this demo is that once we actually run this model and we have our metrics and we display all of it, we can actually go down here to Python PDB, which stands for Python Debugger, and this is essentially lets the users who are a little bit more experienced with Python to actually explore this this data set a bit more. So there are a few key functions which are outlined a little bit more in our Jupyter notebook, which let you play around with the data some more. For example, if we wanted to predict specific instances of the data, we can do the predict, we can type in model, and we can pick in, let's say, the first 5 values of this data set, and we pick X for the data set. And notice that we now predicted the first 5, which are isotopes for all 5. So again, if you're a more experienced user, you can sort of play around with these functions, and these are outlined more in the Jupyter notebook. And if you feel particularly adventurous, you can go to the main Python file, which has these features, again, which you can find in documentation. But for those of you who aren't as experienced, that's okay. There's still a lot of great tools you can explore that don't require you to do anything with the Python debugger. Of course, if you don't want anything, you don't want to see it again, you're simply just going to hit exit, and that will exit out of this program. And then just like that, you're now back in your main directory, and you're now free to do something else. Like if we wanted to, run a different kind of experiment. Let's say we wanted to, instead of model SVM, we could do something like gradient booster. We type GB for that, and then we can run this. We can do the same thing we did just here with a different model, and it really is that simple. So you can do a ton of different classification problems or projects very quickly. You can do multiple runs and experiments on the same data set very quickly, and that's really the beauty of this program, is that you can do all this very quickly, and it's you can get quite a few nice results from just what we have here. And this, of course, will be upgraded in future releases. So I hope you guys enjoyed this classification demo, and then stay tuned for more content on the rest of Neuralist, and I will see you guys in the next video.